All right, folks. This day finally had to come. I know a lot of you have enjoyed the first few weeks of the class, which has had sort of a philosophical flair to it, but sort of a reality check. We need to get back to the sciencey side of things, and in order to do that in this class, we really need to make sure that we have a good foundation upon which we can build. So the next few days are going to be a bit of review. For some of you, it's going to be old hat and quite easy to do. For others, it might be a little bit more painful. But if you go back to those first couple days of class where we went over the system models, if you recall, everything that we deal with basically involves matter, the stuff of which things are made, and energy, which essentially makes things flow and move and do interesting things within those systems. So today's class is going to deal with the subject of matter. If you go and pinch yourself, everything around you, the physical world, is made up of this stuff. And then in the next few days, we'll cover the topic of energy. So I'll try and move quickly through this. Again, for some of you, this is old hat. You may have taken AP Chem, and this is just going to be very basic. So for you guys, I invite you just to skim through this. But for others who struggled a bit more in chemistry, hopefully this will be a beneficial and comprehensive review. So why don't we get started? So first and foremost, when we talk about this subject, we have to talk about what everything's made of, which is, of course, matter. And defined, it's anything that has mass and takes up space. Now, as you go through the universe, this can be found in two basic forms. There are essentially pure substances made up of only one single type of atom, which are known as elements. And then beyond that, sometimes or more commonly actually, you find combinations of different atoms put together in fixed proportions through chemical bonds, and we call these things which are made up of two or more different elements compounds. Now, sometimes compounds is confused with this next term, which is a molecule, but a molecule specifically refers to two or more atoms. They could be the same, they could be different, which are held together by a special type of bond, a covalent bond. So just as an example, if you were to take, let me get my pen. If you were to take, give me 1 second here, sorry. Okay, so if you were to take NaCl, which is common old table salt, you have Na, which is an ion, and Cl minus, which is another ion. Now those two consist of two different atoms or elements, but they are ionically bonded. So these two would be a compound, but they would not be a molecule. If you were to look at O2, which is oxygen, those are two oxygen atoms which are in fact covalently bonded to each other. So oxygen represents a molecule, but it does not represent a compound because, again, these are two of the same elements, not different elements. And then you have commonly H2O, which we all know as water. Well, these are covalently bonded, and it consists of two different types of elements, so this would be both a compound and a molecule. So I know a lot of kids get confused by that terminology sometimes, so just make sure you can distinguish between them. All right? Good. All right, moving on. So I've already used the term a few times already, but if we're talking about the building blocks of matter, the one we most commonly refer to is the atom. Now, certainly there are particles smaller than the atom, which we'll get to, but when we're talking about the smallest unit of matter that exhibits the characteristics of that element, you're talking about the atom. So you can't break an atom down any further and still have the properties of that element. But as I mentioned, atoms are made up of smaller particles, and those particles involve the proton, the neutron, and the electron. Now, the charge of a proton, I think most of us know, is positive. The charge of an electron is negative, while the charge of a neutron is no charge. It's neutral. As far as the mass goes, or the weight, again, we're talking about incredibly tiny particles, and so we had to create a special unit of mass when talking about these things. So the standard unit is known as an AMU, which stands for an atomic mass unit, and the proton weighs in at 1 AMU. The electron is incredibly tiny in comparison to a proton. It does have a tiny bit of mass, and I have to be honest with you, I don't know the exact mass, but it's something like minuscule, like 1/2000th of an AMU. So for most purposes, you can sort of assume that the weight of an electron is negligible, but it does have some small mass. And then to finish it off, you have the neutron, which weighs slightly more, ever so slightly more, than 1 AMU. Now there's something interesting here that I'm kind of surprised most students aren't aware of. I don't know if they just haven't been taught this previously, but if you look carefully at this table, you notice a pattern, right? So you have the positive proton, the negative electron. Well, we all know when you add a positive and negative, the two cancel out and you get no charge. In addition, if you were to look at the masses and you take this 1 AMU and then this amount that's ever so slightly more than 1 AMU, you add those together and you get a mass slightly more than 1 AMU. So again, if you may have been aware of this already, but theoretically speaking, when we think about this particle, the neutron, it actually represents a proton and an electron essentially fused together to form this particle. And it's just kind of a neat little idea in and of itself. However, this will also become very significant to us when we begin to talk about nuclear chemistry. Now, to finish off the table, then, we also want to talk about where these things are located. The proton and the neutron are both located in the center of the atom, in an area known as the nucleus. I can't tell you the number of times that students confuse the nucleus of an atom with the nucleus of a cell. So please don't make that mistake. Even though they both represent sort of the center of these structures, there's a big, big difference between an atom and a cell. While the electrons sort of are zipping around in these clouds or orbitals at these, precise distances away from the nucleus. So some models sort of suggest it looking almost like, the sun in our solar system would be the nucleus with the planet zipping around in these orbits. It's not quite like that. I would say a cloud in which these electrons are zipping through at the speed of light really is a better characterization. But again, I think most of you have taken chemistry and you know the basic structure of a typical atom. Now, if you were to look at a periodic table, you notice all the different structures and symbols, and you'll have, say, a box on the periodic table with an atomic symbol and usually two numbers. One of those numbers is big and one of those numbers is small. I wrote those backwards. But the question is, what do these two numbers represent? And the first one is the atomic number, the smaller of the two numbers, and that really just represents the number of protons that are found in that atom. Now, the number of protons is very important because that is what specifies the identity of a particular type of element or atom. If you change the number of protons, you've essentially changed the element into something else. You can change neutrons and get something slightly different. You can change electrons and get an ion, but you change the number of protons and you've changed the element's identity. The other number, the larger of the two, is the atomic mass. And that's just basically the total mass of that atom. It's the protons plus the neutrons plus the electrons. Keep in mind the electrons are essentially negligible, so really the atomic mass is you add up the protons, you add the neutrons, and there you have the mass. Now this could vary for different atoms of the same element because you have what are known as isotopes. And isotopes have essentially, again, the same atomic number, same number of protons, but the number of neutrons can vary. And so just some examples of this, you have your normal old hydrogen atom, which is just H1. There's one proton and actually 0 neutrons. But you also have deuterium, which is one proton and one neutron, so it has a mass of 2. And you even have tritium, which has 1 proton and 2 neutrons. So again, same element, it's all hydrogen, but these are isotopes of the element hydrogen. And perhaps one that you're more commonly familiar with, or you've heard of more commonly, is carbon-14 versus carbon-12. Carbon-12 is the more typical form of the isotope found in nature, which has 6 protons and 6 neutrons, therefore giving you 12. However, you also sometimes find carbon-14 in which you have 6 protons and 8 neutrons. And carbon-14 is actually significant because it helps us to radioactively date fossils and other sorts of findings that we pull out of the ground. So I just alluded to one of the uses. We use radioactive isotopes in order to date things accurately. So radioactive dating through the use of something known as the half-life, which we'll get through a little bit later. But there's also a very interesting use of radioactive isotopes. We have various equipment, technology devices that can accurately detect the presence or absence of certain radioactive isotopes. And so we often use them as tracers, either in the human body for medicinal purposes, and also environmental tracers. So for example, you can inject someone with a radioactive isotope in their arm and then literally trace or track where those atoms move to in the body. So, I might have injected something into my forearm, and then through the use of these devices, we can find that those atoms injected there have ended up maybe in your brain or in the base of your foot. And same thing with the environment. We can introduce some atoms in one part of an environment and track them or trace them to see where they ultimately end up. And that's actually a very, very valuable tool. I mean, it's very difficult to see or keep track of a single atom, but these radioactive isotopes allow us to do that. Okay. Now, another important concept is the notion of an ion. Okay, sometimes the number of electrons in an atom changes, and actually it happens quite often because atoms like to achieve a certain balance of electrons in their outer orbitals or clouds. So an ion is really just atoms or combinations of atoms that demonstrate an unbalanced electrical charge. It's unbalanced because if you have more electrons than you have protons, due to the fact that electrons have a negative charge, that atom will have a slightly negative charge as well. If you have more protons than electrons, it's the reverse. You'll have a positive charge. So if you were to gain an electron, remember, it's confusing because I'm using the word gain, but if you gain an electron, you gain a negative charge, and therefore you would become what's known as an anion, which is a negatively charged ion. If you lose an electron, now you have more protons than electrons, and you become a cation, which has a positive charge. Now, something else you should note is that you may find atoms, single atoms, that have an ionic charge, and we call these monatomic ions. So a good example would be chlorine, which would be Cl-. But you can also have polyatomic ions, so things such as, nitrate ion, so NO3-. That 3 should be a subscript, but this is a collection of atoms which are actually bonded together. But if you were to take all the protons and all the electrons in that molecule, collectively there's a slight negative charge. There's one more electron than there are protons. And you can also have positively charged polyatomic ions. But the point being, you can have a single atom or multiple together that have an ionic charge. Now, atoms often don't stand alone in nature. There's actually a very small number of atoms, the noble gases, which remain sort of independent as single atoms. Most atoms like to sort of combine with others, and the way in which they combine are through things called bonds. So atoms or molecules can be held together through these weak or strong attractions. What are the different types of bonds that exist? There are a number of them. Some of the weaker bonds are what are known as hydrogen bonds. A hydrogen bond and a van der Waals force are not exactly the same, but they're both representative of a very weak intermolecular attraction. The hydrogen bonds are between polar molecules. Van der Waals are typically between nonpolar molecules. And if you have no idea what I'm talking about right now, we'll get to that in just a little bit. The reason I'm making a fuss about this, though, is hydrogen bonding is incredibly important to the properties of water that we see in nature. And without those particular properties, we probably could not have life as we know it here on planet Earth. The next one would be what's known as an ionic bond, and that's an attraction between two atoms or compounds that have opposite electrical charge. So like Cl minus, as we mentioned before, along with Na plus or sodium, Na plus, Cl minus, put them together, and you have table salt. The next one involves a sharing of electrons, but it's an unbalanced sharing, okay? So when the electrons are shared in this unbalanced fashion, we have what's known as a polar covalent bond. The covalent refers to the fact that they are being shared, but the polar refers to the fact that it's an unequal sharing. It's kind of like when my older brother and I used to have toys. My brother would share them with me technically, but somehow he always had them much, much longer than I did. Now, this occurs because there's a property in atoms known as their electronegativity. This sort of demonstrates how strongly that those atoms are able to pull electrons towards them. You're going to find that oxygen has a very, very high electronegativity. It's kind of like being a huge, huge weight man in a tug of war. They're very, very capable of pulling that rope towards them. But in the case of atoms, they're pulling electrons towards them. Now, if you have oxygen, which is very strong, going against sort of a medium weight guy, as in hydrogen, there's an unequal sharing, and so you end up getting a polar covalent bond. So then next on the list would be the condition you have when it's a balanced sharing of electrons, which is a nonpolar covalent bond. And again, this is just sort of having a tug of war in which both teams are basically equally matched, and you have a draw, essentially. No one pulls the electrons more strongly towards them, so you have this even sharing. So a molecule like O2, oxygen, both oxygens obviously have the same electronegativity, so when it's an equal pulling and therefore a balanced sharing of those electrons. And that bond can be regarded as being slightly stronger than the polar covalent. And then the last one, which we'll mention, is a metallic bond. And this is kind of difficult to describe at times, but in a metallic bond, it's probably actually easier to draw. So let me see if I can do this for you. Iron's a metal, right? So iron's represented by Fe. So imagine you have an iron nucleus, another iron nucleus, another iron nucleus, and this would just go on and on and on. Billions and billions and trillions of these different nuclei, right? In a bar of iron. Now, the electrons are floating around these atoms, but even though this iron atom has its own electrons associated with it, the electrons just start to freely flow all the way around, every which way. It's almost as if all the electrons are shared by all the atoms in this block. And why is that significant? Well, if you think about a particular property of metals, they are able to conduct electricity. And as we'll learn in the next couple of classes, electricity is essentially just the flow or movement of electrons from one place to another. So if these electrons are able to freely flow all over here, that means that they serve as good conductors of electricity. Okay, so that's just a very quick review of bonds. Again, the expectation is you've taken chemistry, you know some of this. This is more to just jog your memory, but If at any time you have any questions about this, please write these questions down so that we can spend class time focused on your particular questions to answer them. All right? So always keep that in mind when doing these sorts of at-home lessons. Now, next on the list is this notion of acidity. Acidity refers to the concentration of hydrogen ions in a solution. Actually, it really is the concentration of the ion H3O plus, which is known as the hydronium ion. Hydronium. And really all that means, though, is when you have H plus ions in a solution, they immediately combine with a water molecule to form H3O plus. It's much more convenient to just talk about H plus concentration, but I know on the AP exam they've asked, technically what is acidity? It's the measure of the hydronium ion concentration. Now, any substance that will add H plus or remove OH minus to a solution is known as an acid, right? So anytime you increase the H plus or lower the OH minus, it's an acid. Conversely, anytime you add OH minus or remove H plus to a solution, it's known as a base. And sometimes you'll see it not referred to bases, but alkaline. You'll see the term alkaline, which is also referring to bases. Now, you also should probably know that the pH scale ranges from 0 to 7, which 7 being neutral, and then from 7 to 14. And we'll talk more in class, I think, about what these numbers actually are referring to. They allude to the concentration of these different ions in solution. But I always get the question, can you go lower than 0? Can you go higher than 14? And the answer is actually yes. This scale is based on a 1 molar solution of a particular substance, but you can go beyond that to have extremely, extremely dangerously strong bases and also very, very, very strong acids. So 0 to 14 is based, again, on this 1 molar solution, but you can actually surpass the 0 to 14 scale. Not many people realize that, but it is true. Okay, now, in this class, we deal a lot in biology, and so we'd be remiss if we don't talk a little bit about organic chemistry and organic molecules. Now, organic molecules contain essentially the element carbon. Whoops. And, you can even debate whether or not methane is an organic molecule or CO2, but pretty much if it has carbon, you can refer to it as an organic molecule. Why is this significant? Because most of the important molecules in your body are considered organic molecules. However, there is one exception to this. The substance that's probably most abundant in your body, that is most abundant in your body, is water, H2O. So if I was to ask you, is water an organic molecule? While it's very important to living things and organic things, if you would use that term, the technical chemical definition of organic means containing carbon, which water does not. Now, the other important elements to life include hydrogen, oxygen, nitrogen, sulfur, and phosphorus. You basically take these basic ingredients, combine them in any different manner of ways based on their bonding rules, and you come up with the major molecules that make up the living body. Now, there are 4 major macromolecules. Those include the carbohydrates, which are an important source of energy. They also include the lipids, which are your fats and oils, but also, when you talk about cell structure, the phospholipid bilayer falls into this category. Next on the list would be proteins, and proteins serve any number of important functions in the body, from structural proteins like you have in muscles to enzymes, which control chemical reactions. So if you were to pick probably the most critical one, proteins would be it. But needless to say, without all of these molecules, you could not have living creatures. The fourth on the list are the nucleic acids. That's like your DNA and your RNA, but it also includes ATP, adenosine triphosphate, which is a very important energy molecule inside of cells. And then coming back again, the molecules of life, all four of these are organic molecules. They all include carbon and some combinations of these other additional elements. But water, again, water is not an organic molecule, but it is most certainly an important molecule to life. In fact, when scientists search for life elsewhere, the precursor is usually looking for water first, liquid water. Now, water, as I alluded to earlier, has very, very important and unique properties which have made it possible for life to exist on this planet. We'll return to these throughout the year, but for now, keep in mind, water has a high specific heat. This essentially means that water is very good at resisting changes in temperature. It warms up very slowly and it cools down very slowly. And this actually has very important regulatory effects in ecosystems on this planet because it sort of provides stability, what we might refer to as homeostasis, in natural systems. And well, we'll get back to why it does this, but it's a common answer for almost all of these different properties. The other, or next property, is that it has a high heat of vaporization, which is somewhat related to this notion of specific heat, but what it really means is that it requires a lot of heat in order to convert liquid water into water vapor. This has relevance also to why you sweat, as energy is basically stored up in those water molecules on your body, and as they evaporate, they take away a lot of the body heat with it, and that's why you get a cooling effect. If you're sweating, though, and it's a very muggy day out, and it's very humid, and there's nowhere for that water that's on your body to go, because the air is so saturated, you notice you're uncomfortable, you're still hot, and everything else. It's because that energy stored up in the water on your skin is basically staying there. It's not evaporating away into the surrounding air. Next is that water is a very good solvent. It's very good at dissolving lots of things, namely ions and polar molecules. But you also should be aware it doesn't dissolve everything. There's this notion of like dissolves like. Well, water is a polar molecule, so it will not dissolve nonpolar things like oils very, very well, if at all. It is found in all three phases on Earth, solid, liquid, and gas. And yeah, and then you've heard of surface tension, adhesion, cohesion. This refers to the attraction of water molecules to one another and to other things. The solid state, basically ice, is actually less dense than liquid water. Therefore, ice floats. If that did not happen, again, life on this planet probably could not exist, and I can explain that a bit better when we're in class. And now getting to why water has such cool properties and interesting properties, again, it's because water is a polar molecule. That means it has an imbalance in charge, so part of the molecule is slightly negative, part of the molecule is slightly positive, and that basically means the water molecule acts like a tiny little magnet. And so these tiny little water magnets interact with one another, causing these weak hydrogen bonds between them, and it's those weak hydrogen bonds which give many of these interesting properties to water. I keep mentioning polar, nonpolar. Another term you might see that refers to this is if molecules do dissolve well in water, they tend to be polar or ionic, but we call these hydrophilic, while those that repel water, do not dissolve in water, are hydrophobic. Now, matter changes. Things are not static. Things are always sort of dynamic and going from one form to another. But there's two types of changes that will occur, which we'll talk about. But when we're getting to the basic laws and principles of this class, one very important one is the law of conservation of matter. What this basically states is that atoms during a physical or chemical change are neither created or destroyed. In other words, the matter that was here back 4 billion years ago is still the same matter that's here today. It's gone through changes. You know, it might be connected to different other atoms, and so the form might appear to change, but those atoms are still essentially here. The exception to this rule would be nuclear changes, which we'll talk a bit about later. But in physical or chemical changes, no atoms are created or destroyed. Now, getting to physical changes, this is a change in the physical form of the matter, but there's no change to the chemical composition. So we talk about water a lot, which is H2O. Well, H2O can be found in a solid form, in which the atoms are closely packed in a very orderly arrangement. Then you have your liquid, where they're less packed, heat it up more, add more energy to it, turns into a gas. And the point being, you still have H2O here, H2O here, and H2O here. It's just the way those molecules are arranged is slightly different. But I haven't changed the chemical composition in any way. So these are physical changes. These are typically the three states of matter most often talked about, but one that will actually play a role in this class is the fourth state of matter, which is plasma. You convert from solid to a liquid to a gas by adding energy to those molecules, but if you keep going and add huge amounts of energy to the gas, the electrons on those atoms essentially get ripped off, so that you now have just these positively charged nuclei, and then these negatively charged electrons just all zipping around in this gaseous soup, which we call plasma. Super high energy, and in fact it is the most abundant matter in the universe, or form of matter, because this is what you find in stars and in our sun. And since those are essentially the largest objects making up the physical universe, there you go. Plasma is the most abundant state of matter. How does that pertain to here on Earth? Well, if you've ever seen a lightning bolt, that energy rips the electrons off the atoms floating in the air, and therefore a lightning bolt is a form of plasma. And more specifically to this class, we're going to talk about plasma arcs as a potential way to eliminate toxic or hazardous waste, because if you can zap those harmful chemicals with plasma, you basically are ripping those atoms to their pure elemental forms, and any sort of toxic combinations of elements that are forming these bad compounds can be eliminated. So again, more on that later, but if you were never aware of plasma, there you have it. Now, chemical changes then are changes in which the chemical composition of the elements or compounds are altered. So I like to think of it as like different Lego pieces. You know, you take a blue Lego, a red Lego, a yellow Lego, you put them together, you get some combination. Well, during a chemical change, you break all those Legos apart, and you combine them with different other Legos of different colors, and you've got something completely different and new. Now, the atoms are still there. The atoms are still changed. They didn't disappear or appear. It's just basically rearranging the atoms into new combinations. Now, some of the examples of these types of chemical changes involve acid-base reactions. We'll talk a lot about oxidation reduction. Precipitation reactions are basically when something in solution solidifies and drops out of solution. But I think most often we'll be talking a lot about combustion reactions, which is essentially just burning something in the presence of oxygen. Quick little trivia question. Again, sometimes we just don't think about these things, but where did all these atoms that make your body, that make the earth, where did they come from? And again, maybe I could talk more about this in class, but the short answer to this is they came, or they formed, inside of stars and were dispersed through the universe during star explosions or supernova. All right. This, so far, everything we've covered is probably pretty much old hat because of what you've covered in chemistry in previous years. Now, I think you may get to a little of this in chemistry as well, but perhaps not so much, and these involve nuclear changes. This is when you actually change the nucleus of an atom in some way, shape, or form. And, normally, immediately what pops into your head when you hear of a nuclear change is a nuclear bomb. And that's true, and we'll talk about those, but there are other types of nuclear changes as well. Now, the first of those involves what's known as natural radioactive decay. I'm sure you've probably heard of like some substance oozing radiation or giving off radiation, or radioactive waste or something along those lines. And essentially, what that substance is doing is it's giving off these various forms of radiation. But radiation can come in basically three different forms. Two of those forms are particles. One of those forms is essentially pure energy. But what happens is, in certain nuclei of certain atoms, there's just too many neutrons, or there's an imbalance of the protons and neutrons that are in there, and the nucleus is unstable. It wants to become stable, and the only way of doing that is to give out or give off something from inside of the nucleus. So the first type is known as an alpha particle, and what that essentially consists of is a particle made of two protons and two neutrons. It's in effect the same as a helium atom nucleus that's being given off, and that's an alpha particle. The next one is a beta particle, which is a fast-moving electron emitted from the nucleus. Now, this one sometimes confuses people because we're talking about the nucleus, and we've just said that an electron gets emitted from the nucleus, but electrons aren't in the nucleus. Electrons are floating around in these clouds outside of the nucleus. So where does this come from? Well, this is where that neutron comes in. Remember, earlier in this lesson we said that a neutron essentially is a proton and an electron smushed together. Well, if the neutron gives away its electron component, what's left is actually a proton. So you can convert a neutron into a proton by eliminating the electron component. And that's actually what happens in certain nuclei, and we call that beta radiation. I will note at this time, sometimes you see pictures of nuclear power plants, or you've seen The Simpsons, and you got Homer Simpson who wears those big radioactive suits. Those suits are designed to basically prevent penetration from alpha and beta radiation. So it is protection when exposed to radioactive material from these two forms. However, those suits don't really do you any good to protect you from the third type of radiation, which is known as gamma radiation. And this really is just high energy electromagnetic radiation. It's pure energy being shot out from the nucleus of a cell, and of the nucleus of an atom. And this can penetrate your body, zap your DNA, scramble your DNA, and cause some really, really terrible side effects. These two can as well, but gamma especially, there's very little protection from that. Really, the only way to protect yourself is to limit your exposure. So, in nuclear power plants, when you go to work in a particular high radiation area, you're accurately timed as to how long you're working in that environment. And I forget what the exact regulations are, but for certain types, you can only be exposed for a couple minutes per year, let's say, or not even that much in some cases. So going back to this, these unstable isotopes, these atoms with extra neutrons or whatever in them, are called radioisotopes, and they will start to give off these forms of radiation to try and become more stable. And the rate at which that happens is a very regular, precise rate known as the half-life. And the half-life is the time it takes for half of the nuclei in that substance to decay. Now this is significant because when we talk about radioactive waste, it usually is considered to take about 10 half-lives for a substance to go through before it's been broken down to such a small amount that it could be safely stored and so forth. that it's not really posing any significant risk anymore. But different elements or different isotopes have different half-lives. So iodine-131 is an example of a radioactive isotope whose half-life is only 8 days. So if you take the 10 half-lives rule, 10 half-lives times this 8-day half-life would give you 80 days that you would need to be protected from this particular isotope before you can sort of consider it to be harmless again. This is important because if there was ever a nuclear attack on us, we have these storage bunkers and everything else, and one of the things that's provided are iodine tablets. And the idea is, in a nuclear blast, some of this radioactive isotope would be emitted, but if you take the iodine tablet, it would prevent your body from absorbing this particular radioactive form, and that would confer protection. And you would need to do that, according to this, for about 80 days before it could be deemed safe. The sad part about all that is that there's other forms of radiation that you're probably getting bombarded with, so protecting you from iodine is good, but it's probably not good enough. But going beyond that, contrast that with plutonium. Okay, plutonium is one of the byproducts of nuclear reactions in our nuclear power plant. So this is an example of the radioactive waste that's left over that we need to deal with. Now, its half-life is 24,000 years, not days, but years, right? And if we take that 10 half-lives rule, 10 times 224,000 gives you 240,000. And so what that means is that radioactive material would be essentially incredibly hazardous for 240,000 years. And it would take that long before we can sort of deem that material as safe again. So when we talk about storing or protecting ourselves from radioactive waste, we need to guarantee safety for the next 240,000 years. That's a very long time to try and monitor and maintain a particular substance. I mean, there's no telling whether humans will be around for another 100 or 1,000 years, and yet we need to figure out ways of keeping that material under wraps for that long period of time. So that adds to the sort of debate or the controversy over radioactive waste and nuclear energy. Now the next two, just quickly, involve probably what are more familiar to you in terms of nuclear reactions. There is what's known as nuclear fission. That's where you take a really, really big nucleus and basically smack it with a neutron, and then that very unstable nucleus rips apart and in the process releases energy. And that's what's being shown here. Here you have uranium-235, which is our most widely used nuclear fission fuel source. You smack it with this high-energy neutron, it splits. In the process of splitting, it also gives off a couple more neutrons, which then will hit other uranium atoms which are nearby, which will then themselves split, hit other atoms, and so on and so forth until you create what's known as a nuclear chain reaction. This is the source of basically a nuclear bomb. You have enough material in there, you get the reaction going, and then this cascade of energy is released in an almost instantaneous amount of time. But we do this in nuclear power plants as well, except what we do differently is we control the reaction through the use of substances called moderators and control rods, which absorb neutrons. So the idea is we get a reaction started, starts to release energy and heat up, but rather than letting it just snowball out of control, these substances absorb the neutrons, the excess neutrons, and they stop the chain reaction, or at least control the chain reaction, so that you don't have these big explosions at nuclear power plants all the time. But the other type of nuclear reaction is known as nuclear fusion. And this is essentially the reaction that's taking place inside of stars all the time. This is where you essentially take two smaller elements or atoms, such as hydrogen, and under extreme conditions of temperature and pressure, rather than bond chemically, these two nuclei actually fuse together, hence the name fusion, to become a heavier nucleus. and therefore a completely new element. So you can smack together, under these conditions, these two hydrogen atoms, deuterium and tritium, and presto, now you have helium with a little neutron given off. The amount of energy released in these reactions is pretty astronomical, and you'll also notice there's no radioactive waste that's left over. You got helium at the end and a neutron's floating around, but there's no radioactive isotope like plutonium that you need to deal with at the end of this. So for that reason, nuclear fusion has one up on this nuclear fission process, and the process we use in nuclear reactions, in nuclear reactors today to make electricity, is nuclear fission. We're working diligently on trying to master nuclear fusion, but right now it's very difficult to create the conditions needed to start that reaction. But the idea is if we could ever master nuclear fusion, that will solve most of our energy problems from here on out. Okay, I know this is going on a little bit. We got a little bit more here, so I'm going to blow through this last area. Why do we care about chemistry? There's a trillion reasons I can give why chemistry is important to the study of environmental science. It's basically the foundation for most of the reactions and things happening in an environment, but two very specific ones that we're going to deal with a lot this year involve pollution and resource use. Okay? The effects of and how to treat certain types of pollution are highly related to the chemical properties of those substances. Beyond that, though, an important concept that we'll go through over and over in this course is the notion that because matter can really not be created or destroyed, there is no way. I mean, in other words, when you throw something out in the garbage, when you throw matter or atoms in the garbage, someone picks it up and it's out of your life, but it doesn't just disappear. It has to go somewhere. Sometimes that's the ocean, sometimes it's a landfill, but the point being, everything that we consume and create and personally toss has to end up somewhere. There is no way. And just keeping that in mind is important when considering sort of notions of recycling and those sorts of things to deal with our waste issues. Now, on to pollution. You got to know this for the upcoming test, and again, this is just the foundation, but when you talk about how bad or good a pollutant is, there's really three factors that you want to take into consideration. The first one is its potency. In other words, how harmful or reactive is that actual substance? Is a piece of paper a pollutant? Yeah, it could be, but does exposure to a piece of paper mean that I'm going to get a neurological disorder? No. Exposure to something like mercury, however, does mean that I might have some really, really terrible harmful reactions. So first and foremost, potency of that pollutant is important. The next factor, though, involves something known as persistence. And that essentially refers to how long that pollutant is going to stay in the environment, whether it's in the air, water, etc., or even your body. Now, some pollutants biodegrade or break down very quickly. Others almost never break down. So you want to try to avoid, whenever possible, the ones that don't degrade. Some terms related to this involve whether or not something is degradable, something that can be broken down completely. Again, it doesn't disappear, it's just whatever that substance was in its more harmful form gets broken down into smaller and smaller compounds, molecules, etc. More specifically would be the term biodegradable. That's essentially when living organisms are able to break down a substance of some kind. Lots of decomposers will do this, and in many cases those decomposers are bacteria. We'll talk about the BP oil spill later in the year and the fact that that oil actually was largely broken down or cleaned up by naturally occurring bacteria. The next one involves something that is slowly degradable. That's a situation in which it would take decades or even longer for something to break down or degrade. We've mentioned DDT as an example of this, as being a pretty persistent molecule. which is why it was considered so dangerous. And plastics will degrade over time. They'll actually do something known as photo degradation, in which sunlight will slowly break it down. But in some cases with plastics, that can take hundreds, if not thousands of years. But then you also have non-degradable. And that's in which, you simply cannot break that substance down through natural processes. And this often involves heavy metals, things like lead, mercury, arsenic. In some cases, they're already in their elemental form, and there's no way to break them down whatsoever. And so these, as I said, are really the bad ones. These are the ones we want to avoid because, again, they usually are very persistent in the environment. And a lot of these also have pretty high potency. If you do ever run into a situation where you have some non-degradable substance, is there any way of dealing with it? So different methods of remediation could include the following. But keep in mind, these are also methods which are often very expensive and very difficult to do. So there's a sort of rule of thumb in environmental science that you want to prevent the harm first rather than try and clean it up after the fact. It's always better to prevent it than react to it. But one method is known as oxidation. It's where you expose things to a lot of oxygen usually. Since the oxygen is so highly reactive, it often will convert whatever the compound or some substance is into a less reactive or a less harmful form. It may not be perfect, but it's better than having like the purely toxic substance out in the environment. Another one involves precipitation. That's where you have some sort of pollutant that's like fully dissolved, say, in a pond or in some other liquid, and by adding some other form of chemical, that substance that was dissolved falls out of solution. It starts to coagulate or solidify, and at that point you could potentially filter it out of the liquid, or it will settle to the bottom of the liquid, and then you can physically collect it, perhaps move it to a secure landfill or something else, or treat it. But when it's in solution, you really have no way of dealing with it. So this gets it out of solution. And then the last one is known as neutralization. This would most commonly apply to acids or bases released into the environment, and you perform a neutralization reaction. So if you have an acid, you add a base, it neutralizes, and you're good to go. But getting back to the three factors, we had potency, persistence, and the third one is concentration. So in other words, how much of that stuff is in the environment affects how serious a problem it is. So it once was, actually regarded as, today we have reduce, reuse, recycle is sort of the environmental mantra. There actually was a time where the mantra was dilution is the solution to pollution. And the idea was pretty much just dump your trash in the ocean, and because the ocean's so big, it will dilute any pollutant down. And of course, we sort of learned that, that's not the best policy, because the ocean is not limitless, and the amount of stuff we're adding to it is finally catching up with that. So you can have parts per thousand, parts per million, parts per billion, and so on. And the idea is the more dilute it becomes, or the less concentrated it becomes, the less harmful. But there are even exceptions to that rule, in which there are certain substances that even in the smallest traces can be harmful. Okay, and then finishing up. When we talk about resource use, again, resources are typically different types of matter, whether that be metals or plastics or what have you. But there's a concept known as matter quality that's worth discussing briefly. And it's the idea that, not all resources are created equal. How useful a resource is to us depends on a few different factors. So you will have high quality matter versus low quality matter. And the difference being, high quality matter would be things that are highly concentrated. They're usually easy to get or extract from the earth, so they're usually near the surface, and there's a lot of great potential for use of that. Low quality, on the other hand, is very dilute or dispersed. It's often deep underground, hard to get at. It provides little potential use for us. So just as a quick comparison, if I had an aluminum can in my hand versus aluminum ore, and aluminum ore basically is little tiny specks of this stuff interspersed in huge amounts of solid rock, right? So if I was to compare the quality of these two forms of aluminum, well, this is a much higher quality form because it's concentrated, it's easy to process, it's easy to get at, where this takes a lot of energy and everything else to process. There's a whole list of these: table salt versus salt and water. Again, table salt's more concentrated, all those sorts of things. So you have high quality matter versus low quality. Obviously, I think we would argue that we desire more high quality forms of matter, but the problem is, and this is a economics concept, there is the law of diminishing returns. Humans have a tendency to go for the easy bit first. So, when we talk about resources on this planet, we've sort of already gone and exploited most of the high quality matter that's been available to us. You used to be able to dig down, like in Pennsylvania, where some of the first oil wells were found. You can dig down just maybe a few dozen feet or less than 100 feet, and you would strike oil. But we've used up all those easily accessible oil reserves. Now we need to drill miles, in some cases, beneath the surface of the earth, thousands of feet, in order to get to oil as well. So again, the additional benefit, it's the idea that the return on investment diminishes because all the best resources are essentially used up first. And why is that significant to our discussion? It's basically because, look, we need additional resources to continue running the economy and the global system we have today. But as we move forward, it's only going to get harder and harder to extract those resources from the earth at greater cost to us and so forth. So, whatever challenges we have with respect to oil or some other resources now, chances are it's just going to get harder as we move down the road. Okay, a lot of material that was a bit longer than I had hoped. Again, hopefully it helped you guys who despise chemistry or have forgotten a lot of it. Hopefully it was a good refresher. But please jot down your questions, and we'll spend the next couple of classes clarifying any of the material that you're struggling with still from this lesson. All right, take care.